In this tutorial, we'll go over the PC lab that was disrupted due to the room not being adequate with the lack of PCs. It's a different data set to the one that's provided. To give it a different example, because we've covered the UK GDP data we've looked at quite a lot in the lecture. So this is US GDP growth from 95 till 2017 quarterly data, and we plotted the graph here. So to do this, you double click the series on the work. If you're using Eviews, you double click the series label in the work file. Then you click view, you click graph, and if you just want the standard graph like this, you just click OK and it'll print this for you. If you want, there are other options. You could add a line for the mean, so you could work out the mean and have a line added somewhere. You can change the colors, you can add more plots, you can change the labeling, the scalings, and so on. Okay, so what can we see then from the properties in the graph? Well, again, the main things we're looking for, as always, it's the properties of the mean, the variance, and the covariance. Specifically, especially in terms of stationarity, are they staying the same over time? We're just looking at the individual, and again, other things you might look at, are there any outliers? Again, it might be relevant, and so on. So we can see, well, the mean looks to have stayed fairly constant. It's hard to tell, of course, because you can never fully tell. Again, the mean could have changed and you can't notice it at the graph. We can see that this looks to be an outlier here with the financial crash. So this could be just an outlier and not the fact that the mean has changed. Again, the variance doesn't seem to have changed either. Again, it's very difficult to tell here. It doesn't look to have changed. You could split up the sample and test this, but again, looking at the graph, there's not a great deal of evidence of a change in volatility over time. Finally then, for the covariance, well, we can see that it does look to be quite a strong persistence here, and a positive persistence. Namely, if there's a shock above the mean, then it tends to stay there for a number of periods. So the mean is around here. So again, we can see when it goes high, it tends to stay there for a while. When it goes down, it tends to stay down for a while. So there looks to be some evidence of a positive persistence here, going on for quite a number of lags, but not long time. So again, it looks 3 or 4 lags, and they tend to die away. And you can see that again by just taking gaps of 1, 2, 3, or 4, or moving along and seeing what happens when the series shoots above its mean. Does it tend to stay there next period, 2 periods, 3 periods, and so on? So again, there looks to be some positive dependence, quite strong but not really strong, and it looks to die away relatively quickly here. So again, these will be things to bear in mind when we come to look at the Correlogram. Doesn't seem that the covariance function has changed over time. Doesn't look like the correlation structure changing, but that can be hard to tell. But again, sometimes it can be obvious, but there doesn't look to be any obvious change in the correlation structure through time. For example, if a series looked really dependent and then suddenly started looking hard to predict, that would be evidence that there'd been some kind of change in the correlation structure through time. But it's often hard to spot for more subtle changes, so it's hard to tell here, but there's no obvious evidence. Next thing then would be to look at the Correlogram. So again, if you're using eViews, then you click in the window that you have open. When you're in the graph window here, you click on view and then click Correlogram. So I think I've got that on I thought I had it on a... Anyway, when you're in view, when you're on the graph page, in the top left hand corner there'll be a button that says view. Click on it, a new menu will open, and one of them will say Correlogram. So click Correlogram, choose a number of lags. So here we've just chosen 16, it's quite a small data set, and a lot of them tend to not anyway. But again, you'd want a sizable-ish number, but remember, the more lags you include, the lower the number of degrees of freedom. So again, we've only got 88 observations here, so we wouldn't want to choose something too large. 16 is probably large enough here. And as we can see, by lags 13, by around here, they've gone to naught anyway, and if you carry on, it's likely that a lot of these are going to be naught. And that was obvious from the graph as well. There's not persistence many periods ahead, not in any strong form anyway. Well, firstly, let's describe the Correlogram output. So we can see by doing just by doing lots of individual tests, we can see that after lag 4, if we do a 5% individual test, we'd find each of these, we wouldn't be able to reject the null hypothesis. So here, if we did individual test, there's kind of no evidence to reject null that the true correlation is 0 from lag 5 onward. Again, doesn't mean that they're definitely all not. Of course, it can be wrong, but again, if they're not, it's likely they're going to be small. So there could be some remaining correlation, but it's going to be small here. Up to lag 4, we would find evidence to reject the null at the 5% level because it's just outside the bands. So again, we would reject the null here, that the first 4 correlations were not. We can also see that by a joint test. The joint test at any lag, but even at lag 4, there's very strong evidence that at least one of the lags up to lag 4 is non-zero. And we can see that as well. They're very far away from 0. It's very likely that at least one, if not all 4 of these correlations are going to be non-zero at lags 1 to 4. Okay, so we found which correlations look to be statistically significant, which ones don't. We then want to look at what's the shape of it. So we can see that up until lag 10, they're all positive, and they're declining overall, but not in a monotonic way. So we can see it goes down from 1 to 2, 2 to 3. It goes up very slightly. We can see that here from 3 to 4, and then down. And again, a lot of these are found to be not anyway. But we can see the first 4 significant correlations do not seem to have a declining correlation. Again, they can be misestimated, so they could be wrong. But looking at it as is, if these were the true correlations, then we can see that they're declining quite slowly here and then going off to naught afterwards. So it's unlikely it's going to be an AR1 process because they're not going down quickly enough. It could be a more complex. It might be, for example, an ARMA 1.4 or an ARMA 1.1 if you allowed there to be correlations at lags 1. If you tried an AR1, it could allow something like this, but it wouldn't be declining quickly enough. We may need to add in other regress into our model. We could add in the shock at lags 1 and 4, for example, to allow for this pattern. Again, it looks though that there are likely to be some AR components here, and it looks like it's not an extremely complex model. So this could possibly be like a low order AR model or an ARMA model. And again, you could try a number of models. It could possibly be an MA4 because the first correlations are not, and then the rest could all be not. So you could try an MA4. To candidate models, I would say AR1, AR2, an MA4, some combination thereof. You could even try an AR4, an ARMA 1.4, and so on. But again, it's going to be a relatively simple model, and I think in this case, considering all ARMA 4.4 models would be a reasonable candidate class of models, and then narrow it in from there. So I'm going to look at some key models here and compare them. I'm not saying that this would be an ideal model answer for a project. I'm just giving you one possible way of looking and analysing this, and it's more to highlight how to use Eviews and to analyse the output. So let's start with an AR1 then. An AR1 is unlikely to be able to model this correlation as it is, because again it's not got the form of an AR1 correlogram, but as a base model it should be able to model quite a lot of this. An AR1 model should be able to pick up quite a lot of this correlation. It's just going to be somewhat off. So we can start with an AR1. To run a regression, you go into your work file, you right click in this space here, and it will open this menu. You click new object, that will then open a new menu here, and you can do all sorts in here. You can make graphs, you can do, when we come to do vars, there's a var option, you can split the sample, you can make an equation, and again you can label it here. So you give it a name, you could save it as AR1. When you're done, it will then make a new output in here, and it will save an equation. Now it will save your estimation output. So we've got the data series here, the dates. So when you double click on this, when you double click say on GDP GGR, it will open up the kind of Excel type spreadsheet with all the data outputs in. And that's where you can click view to look at the graph, and you can also look at the Correlogram by going from there. So double click the white space, opens up a new menu, click equation, save a name, then it'll give you this out window here. Then you've got to specify the equation you want. So again, this part, you can again, if you want, you can change the sample. If you want to split the sample, for example, you could change the estimator, but we're going to be sticking with an ARMA model here, so you won't need to here. So the key part is here. We want to regress. Again, you got the name of the variable GDPGR, which you can change if you want. If you right click on the variable, you can change its name on a constant and the lag of GDPGR1. And an alternative way to write an AR1. So you could do GDPGR C on AR1, which will include one AR1 lag. Okay, if you do this, click on the OK button, then it will do the estimation for you and give you the output that we've been seeing in the lectures. This is then the output. So we've got our coefficient estimates, the standard errors. We've got the t statistics from an individual test that the true coefficient is not, and we've got the p-value. We can see there's extremely strong evidence to reject both that the constant is not and that the coefficient on the lag of GDP growth rate is not. The p-value being, intuitively, the p-value is a probability that the null is true. It's saying that this is kind of 1 in 10,000. So of course it's highly unlikely that the null could be true. So we expected to find this coefficient. We saw that there was quite a strong positive correlation. So although this would likely be a misspecified model, it'll choose, although it's misspecified, it will choose a coefficient on yt minus 1 to make this model fit as closely as possible to the true model. Remember that when we run an AR1, it estimates the coefficients using a regression. So you're minimizing the sum of squared residuals. So although you're going to be choosing the wrong model, it'll still choose the best fitting model. And if you look back at the Correlogram, it makes sense. So it's chosen a coefficient around 0.4, and that would make sense. It'd be able to pick up this first correlation, but then it'd be wrong because then the next correlation would have to be 0.4 squared, and it's not. Remember, it's picked the coefficient to be 0.412, and if you see, it's picked it to be, and this is why, because the AR1 estimator, the coefficient is almost exactly identical to the correlation the first leg. And it does that because, well, then from that, the next correlation will be this squared, and then so on, and then cubed, and then so on. So it's in essence fitting well to the first correlation, but it won't fit the next correlation because in this model, the next correlation with the coefficient of 0.412 will give you 0.412 squared, and we can see it's not that. So this AR1 model will pick up the first correlation, and it'll be somewhat near to the next three, but it's going to be off. And then that's when we've then got a misspecified model. We're going to have to add in more lags to try and capture the remaining correlation that this AR1 model cannot. So that's the way to think about it. So this is a good base model. Again, we've got our information criterion here, should we want to compare them later on to other models. You could then think, okay, we could maybe improve matters by considering an ARMA 1 model. An ARMA 1 model would then free up the first correlation and would allow a more flexible correlation structure. We can run we do the exact same thing again. We generate a new equation, go back to the main screen, the work file, right click on the workspace, new object, equation, and now in the equation you add in an MA1 term. So you run this equation in the, you go back, and now this includes epsilon t minus 1. And this is what it's done here. So this would be the coefficient estimate theta 1, I guess, and phi 1 hat and mu hat, say. We can see, again, there's some evidence now that the constant could be zero, but again, it's not enough evidence to drop it out of the model, and it can cause problems if you drop out the constant when there actually is a non-zero mean. So again, it's not really strong enough here to drop this out. We'd only just accept the null at the 10% level that the mu was not, so we wouldn't normally drop this out here. We can see that there's very strong evidence that both yt minus 1, this has run the regression in essence mu plus d1, this is the ma1 term, plus di1 yt minus 1, this is the ar1 term, which is the gdp jr minus 1, plus the shock. We've got our estimates, and we can see we found a negative coefficient here and a positive one here. Okay, so this makes sense as well then. So this is now going to fit better. So again, we can see that the first correlation again is going to be this one minus this one. It's going to be around, it's going to pick out, we can see it's going to now fit. Both of these are significantly different from 0, so that we've missed out. So this is going to fit better relative to this model here. So in this model, we've missed out this MA1 term that's got a very significant effect. We can then, if we want, in both cases, in any model, if we want to see if the model's a good fit, then of course we need to check whether the errors are serially uncorrelated or not. So there's two things. We can do a serial correlation LM test. We can test that there's no correlation left in the residuals. And again, we know we need that to hold for the model to be well specified. But if there is serial correlation, you can also look at the correlation pattern in the residuals, because then you can get an idea for the kind of correlation in the residuals. And remember, once we know the form of the correlation in the residuals, we can back out what the true form of the process will be. And we gave an example in the last exercise class. We showed that if we run an AR1 model and it's got ARMA 1.1 errors, then the true model will be an ARMA 2.1, and we showed that in the last exercise class. So we might want to look at this. So again, in your estimation window, then you go back, click residual diagnostics, and then you can look at the Correlogram. So in your where your estimation was, you click on view, go to residual diagnostics, and then Correlogram. This is now the Correlogram of the residuals from the ARMA 1.1. So we can see then that we would accept the null at all lags that the correlation residuals is not. So this is then evidence that there's no correlation in the residuals up to lag 8. We can do a joint test by doing the serial correlation LM test to formalize this more. We can, again, you go back to the estimation window, you click on view, residual diagnostics, and then the serial correlation LM test. So again, it's in the same window as before. The Correlogram gives you the plot of the correlations in the residuals. This will do a test that there's no correlation in the residuals. Again, you pick the order that you want to test. Here, because it's quarterly data, we pick lag 4. It now does the LM test. The null hypothesis here is that there's no... The null hypothesis here, when you choose a lag order of 4, in essence, it takes the residuals and it runs an AR4, and it tests whether the residuals are an AR4 against a null. So in the LM test does this. It runs this, it estimates the residuals, it runs this regression. The null hypothesis is that there is no correlation, so all the coefficients are not, against the alternative at least one is not. So the LM test runs the regression, estimates residuals, runs an AR4, and then does a joint F test basically that all of the coefficients are not. If they're all not, then there's no correlation of an AR4 form. We found here then doing this test that the p-value is 0.8635, so we can see straight away there's very strong evidence here to accept the null that there is no correlation in the residuals from an ARMA 1.1. Again, still doesn't mean that it's definitely correct, still doesn't, because it could be wrong. It still doesn't mean that it's the best fitting model either, which we can compare those by their information criterion. So again, you might want to then consider some more models. So you can go now to an AR2, and repeat and run an AR2 regression. Again, both the coefficients are significant here, so this is going to likely fit better than the AR1 because we've missed out this AR2 term. And again, we can verify that it will have a lower information criterion. Again, we can plot the residuals from this regression. We can see again there's very little evidence of correlation in the residuals from the regression, and that's also verified by the LM test. So we found evidence to support the fact that this model also fits well to the data. There's no correlation in the residuals. So we've now got two models, with the comparison we've done then, we ran an AR1 model and we found that I didn't actually do it in this one, but if you take the correlation in the residuals from here, you'll find strong evidence that there is correlation in the residuals. We've then gone on. We've looked at including more regressors. We've included adding an MA1 term, and we found strong evidence to support the fact that's needed, which would refute the AR1 model. We've also found that it's the case by adding the AR2 term. Again, this would also refute the AR1 model. So you could combine the two and see that if you can improve inference by including both models, and then again compare them by their information criterion. But going by the two we've considered, well, the SIC is 1.789 for the ARMA 1.1, and it's 1.788 for the AR2. This would suggest then that the AR2 fits better than the ARMA 1.1, than the ARMA 1.1. So then you could go on and consider more models. You could combine them. You could try something slightly more general. Again, you want to get down to a final model. But you can see here that we're using three things all the time. We're looking at parameter restriction tests to see whether or not including a new regressor is needed in the model compared to another one. We're comparing them based on their model fit, which is something we normally do towards the end. Once you've got a number of models that all have no correlation in the errors, we can select between them by which one fits the best. We're comparing them based upon whether or not there's zero correlation in the residuals. Again, if there's zero correlation, it means we've missed something out for definite. And we've also looking at the correlation patterns in their residuals, which gives us information about what we've missed out. So in some case, in here, when we run the ARMA 1.1 and we plotted the residuals, we saw that there wasn't really much evidence of correlation in the residuals. But sometimes you might find that there is a pattern in the residuals. If we'd have plotted the residual plot here if we'd have plotted the correlation plot of the residuals here and it looked, say, something like this, well, this would suggest that the correlation in the residuals was an AR1 perhaps. We can then use our ideas about what we saw in the class in lecture 2. Well, if we run an ARMA 1.1 and the errors are an AR1, we can show that the true model will be an ARMA 2.1, and that would be higher order argument in the project, is to take the residuals from the plot. You have some kind of idea of the kind of model that could be. You could even work out what model it would be, and then you can put the two things together to suggest another model, what the true model might be, by using the form of the process for the residuals in the model to tell us what the true model would be. So again, parameter restriction test, serial correlation test, and using information from the residual, the form of the process of the residuals, and the model selection criteria. And again, we guided our model selection by the Correlogram in the level itself, in the process itself. We saw it's likely to be some simple AR type model, possibly with some MA terms in it, and it's likely we could have just considered an ARMA 4.4, all ARMA 4.4 models. So your project would likely consider a few more. You'd likely have gone on and combined those two, and you would have tried an ARMA 2.2, say. You'd have gone on and tried some more general models, done some more tests, and you'd have got down to your final solution. But this here, just to highlight how to use Eviews to get the Correlogram, how you interpret it, some candidate models, you run the estimations, and again you start kind of quite basic and then move on and kind of get towards a final outcome here. Okay.